Welcome back to Computer Science 4303. Today we are going to be talking about our first real, information lecture of the term, which is going to be talking about movement in games. And realize again that I'm not going to say this every Thursday, because after this one you should be into the swing of things by now. But after class, so after you've watched this lecture, this week's quiz will be available. And the quiz will be covering Assignment 1 and this lecture, which is movement in games. So if you're watching this on YouTube, then this is available, so go do the quiz. And again, you have until Sunday evening at 11:59 p.m. to do the quiz. So as you saw from the first quiz in the class, the quizzes aren't going to be like super hardcore exam questions, and they're completely open book. So just make sure you do them yourself, and you're not just being fed answers by somebody, because that will be kind of sad if you have to do that for the quizzes. The quizzes are literally open book. You can just go look at the information. The first quiz was all about, like what are some passwords, where do you find this information, a little bit of the actual stuff from the lecture. But quiz number 2 is also going to have some of that flavor in it. So stuff that you needed to know to set up assignment 1, and then stuff about today's lecture, which is about movement in games. So again, those quizzes, I think I really like them. I like making up the questions, and they're just really there. They're not there to really stress you out too much. As you saw, they're only going to take a few minutes, but it's really just something to keep you on track with watching the lectures, right? You don't want to have, like, for example, you don't want to pile up all the lectures to the last minute when assignment 3 is due, and then find yourself like having to watch like 8 hours of lectures to catch up. So those weekly quizzes are just basically making sure that by the end of the weekend, you've watched all the week's lectures. I think they're going to, and I was very, very happily surprised that everyone in the class did the quiz. So that's awesome. Thank you everyone for doing the quiz. All right. So that being said, let's hop into today's lecture, shall we? Okie doke. And as always, this is being live streamed on Twitch, so I just had a question out in the chat that I answered in the chat. But if you have any questions during the lecture, feel free to ask them, and I'll answer them when I feel it's appropriate. Okie doke. So lecture number 4, movement in video games and steering behavior. So this is kind of an introduction to what movement is and why it may actually be useful in video games. So movement in games. Movement, in my opinion, is the most important part of a large number of video games, right? So, I mean, unless you're playing some sort of board game in which there may not actually be any movement, movement allows the exploration of the game world and the interaction with the entities, right? So not only does the player, like the character that you're controlling, move around in the game, but a lot of the time the NPCs and the entities are moving around in the game as well, right? And in my opinion, like, it's not graphics that make a game, it's like good movement makes a good game. So who out there in the chat has ever played a game that looks really good, but the movement just pissed you off, right? And you can't enjoy it unless the movement is like nice and fluid and reaction and like good reaction time. And also, like, the NPCs look like they know what they're doing. Like, who's ever done an escort quest in a game and the NPC just starts like running off in a random direction to attack some bunny or something like that? Like, movement is an important thing, right? And so as a sort of introduction to AI in games, since movement is the most important thing, then let's talk about movement first, since this is, this whole course is about game AI. So here's the main video game movement problems that you have to solve, okay? So if you're making a game that has a lot of NPCs walking around, there's 4 main problems related to movement that you want to actually implement and solve in your game. So the first one is called pathfinding, okay? So if you're at location A in the game and you want to get to location B, you have to somehow calculate a path of how to get from A to B. And, one of the prereqs for this course was 3200, where we did a lot of pathfinding in that course. So we looked at methods like breadth first search. we looked at A-star pathfinding, we looked at reinforcement learning, and we saw that there's a bunch of different ways that we can figure out how to get from A to B in a map. One thing that we didn't look at in that course, which is, very important in video games, is now that you have a path, how do you actually move along that path? Right? So that's called path following, and it's a surprisingly difficult problem sometimes. Like, it's one thing to say, okay, move here, 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 but it's another thing to actually guide your character in sort of a realistic way along that path. Another problem, which you may not think is related to movement, but it really is the physics, right? So how does your character, or how do characters or entities in the game react with the game environment? So for example, you may have a path figured out, but maybe part of that path has like ice on it or something like that. Or maybe there wasn't something that collided there before, but now there is something that collided there, right? So physics is a real part of movement in games. And also, even though this isn't necessarily the domain of the AI person, it's actually becoming more and more relevant in game AI, which is the animation, right? So how the entities look as they're actually moving around. So if an entity is moving straight and then it starts moving to the left, well, I mean, I guess in some older games, it's okay to just have the character like instantly turn around, right? Like say Super Mario Brothers, right? I'm facing right and then instantly I'm facing left if I go in a new direction. But then you go to a game like the Dark Souls series, where in order to turn around, you have to like, your character has to turn a little bit, right? So that animation of like going smoothly from one transition in one type of movement to another type of movement is actually really important. And so that is tied into the movement system in most games. But in this course, we're really only going to be looking at the first two problems here, okay? So there's not enough time to go into these things because the physics and the animation, they're really specific to your game and what your game design goals are, right? So the physics will be different in some games, the animation will be different in some games, but pathfinding and path following are pretty generic problems that we're going to have to look at in pretty much all games. So in this course, we will really deal with AI decision-making for movement. So finding a path and following a path. So why does all this matter? Well, I've got a few examples here for you that I think make a good argument for why movement in games might be pretty important. So here's the first example. This is from... Oh, why isn't this working? Here we go. Nope. Go back. Click. There we go. So here we have some 3D pathfinding that sort of fails in this weird edge case. So this is from Saints Row 3, I think it is, where you see that, like, the 2D pathfinding map, the cars are taking the right path, but as soon as things get a little bit more complicated, they just start falling into the ravine, which is kind of funny. The next example that I have, I'm calling threat-aware pathfinding. My webcam is kind of covering up in the top right here. But this is an example from Skyrim, and Skyrim has some notoriously funny AI in it. But in this example, the character is hidden. And so they're going to be walking through this dungeon, and they move past this trap. And then you might be able to hear in the back some enemy saying like, oh, what's that? And so the enemy reacts to a sound that the player made. And then that the NPC is going to try and investigate. And the pathfinding, this enemy lives in this dungeon, but the pathfinding produces some pretty funny results. So this might be a little bit dark. So the player is sneaking. Is someone there? The NPC says. So there's the NPC oblivious to where the player is, and walks right into the trap. And then the second NPC who just saw that happen right in front of them. So like, whether or not you want that to happen in your game is up to you as the game designer, right? In my opinion, the Bethesda games, the Skyrim games, are sort of known for this sort of buggy AI, and it's kind of an endearing trait to those games. But in some games, you may or may not want that to actually happen. Excuse me. Here are two examples from the original game of StarCraft. And in StarCraft, basically a lot of the game involves moving your units as a group, okay? So in this first example, what we have are a group of tanks. And these tanks are going to be trying to get around this little obstacle in the map. So ideally what would happen in this scenario is that you would select all your tanks, like is happening here, you'd tell them to move, and then all the tanks would sort of move as a group. However, what happened in the original StarCraft Brood War is that the pathfinding assumed that it was a single unit. And so as you saw, let me go back here and restart this. When we selected all the units, what the game did was generate a path for a single tank. And then all of the tanks in the group sort of fight for position along this line. And if you've ever played any RTS game, if there's enemies on the other side here and they're not moving as a group, well, what just happened? Now they're going to be picked off one by one, right? And so these first few tanks, they'll be just getting picked off, and you want to be able to move as a group if possible. And so we're actually going to be doing a group pathfinding algorithm for assignment 2. It'll be really cool. Another example here from StarCraft is, let's say we wanted a bunch of these workers to attack a building, right? But you can see here that this sort of surrounding the enemy behavior is not implemented very well, and we have a bunch of units getting stuck on each other, and only after about 20 seconds or so does this actually get surrounded, right? So that's something that could be improved upon. And if I go here, in StarCraft 2, it turns out they did improve upon this, and very, very well. So this is like strictly an algorithmic change, right? So you can see here the person has about 100 Zerglings selected, and the flocking behavior of the Zerglings is just really amazing. Like, this is really, really cool. And so you can see here that the Zerglings sort of group up and they move together, even when they're moving through these choke points, like they're moving all together, and they're not like fighting for position in a single line. Now, of course, the choke point has a certain width, so they all can't fit through at once. But that's pretty ideal for pathfinding. Like, I couldn't really imagine simulating a flock of Zerglings any better than what's being done in this example. Okay, so that just goes to show you, like, how far we've come from this behavior to the Zergling behavior, right? Also, not only are you concerned with these sort of technical things, like making sure units are sticking together and moving as a group, those sort of like tactical decisions, but you also want like realistic behavior, right? So here we have an example from Dragon Age where these NPCs are just kind of getting confused. Whatever destination they had, this is supposed to be a pretty serious cutscene, a conversation, but in the background, we just see these NPCs moving back and forth. So this is kind of a funny example that later in the course, we may be able to explain something like this. But for now, you're just trying to show that, you want to have realistic behavior, and this is an example of not quite a realistic behavior. Next, I want to set this up just a little bit. So this game is from the Fallout series. And in this game, what's going to happen, well, in this example, what's going to happen is as you move into the range of this NPC, the NPC sort of sees you and then it wants to run toward you, right? So in order to run toward you, it has to calculate a path, and then it has to follow that path. But it turns out that if the player moves up onto this little tiny ramp, the NPC like takes this other path that's probably a little bit suboptimal. So let's see how this works now. So here's the NPC that wants to get to you, but the player, it was right next to you. All it had to do was walk up that ramp, but then we moved on top of this little building. And so here's the NPC, decides to take the scenic route to the player, right? So you can imagine now this NPC is like trying to find you to report their like kidnapped child or something like that, and they had to run all the way around the level just because of bad pathfinding, right? So let's just see what happens at the end. Almost there.
Here.
Right? So that's kind of funny. You want to avoid that if at all possible. And what this thing says up in the top right is that animation matters, right? So no matter how intelligent your pathfinding is, if this is what it looks like, people are just going to laugh at it, right? So let me restart this. So like obviously this horse is just stuck in whatever like T-pose animation or something. And so animation really does matter. If no matter how intelligent, you could write your PhD thesis on this pathfinding algorithm, and then if the horse does this or if the player character does this, it just people think you're stupid, right? So animation really does matter. We won't be going into animation in this course, but just recognize that that animation system should be doing its job to hold up the realism of the pathfinding system. Okay, so we talked about those different problems, and the first one was pathfinding. So, we know a little bit about pathfinding from 3200, but let's just go through it again. What is pathfinding? So, video game maps are often filled with obstacles in which NPCs will collide, right? So, if you just had a big open world and you just had a field with no obstacles in it, pathfinding would be trivial, right? I want to get from A to B. Well, I just calculate the straight line and I move from A to B. And so that's obviously trivial, but in most video games, the environments are not trivial. They want them to be interesting for the player to play. And so oftentimes, there's walls, there's other characters, there's a cactus or something, there's lava, and you've got to go around those things. And so you've got to calculate that. So pathfinding is the method that we use to determine which path an NPC should take to get from its current location to a desired goal location, right? So in that example, the NPC was trying to give a reward to the player, so it was trying to get to the player, so it was trying to get from its current location to a goal location, which is the NPC. Now, it turns out that goal locations, and we'll talk about this a bit later, they could be static or dynamic, right? So that player was actually trying to get to a dynamic goal location. So it was trying to get to the player. So the player might be moving while it's navigating. And so sometimes you may have to calculate a path more than once if it's this sort of dynamic scenario. So basically, every so often, that NPC would have to say, okay, where is the player now? And if the player moved, I'm going to have to recalculate my path to that player. And pathfinding attempts to minimize a cost of the path. So it's not necessarily the case that you want to get to something as fast as possible, right? So it could be that you're trying to minimize the total length. Maybe you're trying to minimize the fuel. Maybe you're trying to minimize the amount of damage taken, or some other arbitrary function. So let's say that you have an NPC that's trying to reach the player, but what happens? Let's say there's some lava in the way, right? So the NPC might have 100 hit points. It wants to get to the player, and maybe in an attempt to attack them or something. But do you want that NPC to possibly kill itself walking over the lava in order to get to the player, right? So it's not necessarily the case that you want to take the most direct path, but you may want to say, well, walk around the lava because we want it to be the least damage taken to get to the player or something like that, right? So pathfinding can do that. As we saw in 3200, we had this A star algorithm, and A star has an objective function, the cost function that we're trying to minimize. And so that cost could be whatever you want it to be. So what are some considerations that we have to make? So let's say that you just started a new job as an AI programmer for some indie video game company. And they say, we want you to make the pathfinding system for our game. Well, okay, so how do you go from that statement, we want you to make our pathfinding system, to actually starting to implement the pathfinding system? Well, there's some considerations that you have to make before you start to actually go in and start like choosing the algorithm or implementing the data structure, etc. So the first one, in my opinion, is whether or not the pathfinding problem is going to be a single agent problem or a multi-agent problem. And I'll show some examples of this. But for instance, is there one NPC trying to get to me, or are there a bunch of NPCs trying to get to me? Whether or not what an algorithm that might be good for a single agent, like the A star search algorithm, might not be good for multi-agent, right? So for example, what StarCraft tried to do in that example was treat everything as a single agent problem. And then in the path following step, treat it as a multi-agent problem. And that might not be the best case, but that's what they tried to do in their game. Second, is there a single goal or is there multiple goals, right? So for example, we might want to get to the exit to a level. There might be a single goal, or there might be multiple goals where we're trying to say, get to the closest health pack, for example. Is it a static pathfinding? So for example, we might be able to pre-compute some paths, or is it dynamic pathfinding that has to be done online, right? So maybe the player is moving and stuff and you have to re-pathfind to them. You have to consider a space representation. We'll talk more about space representations in detail in the next lecture. So there are different types of space representations. Maybe you have a completely arbitrary open representation. Maybe your pathfinding system uses a grid or a graph or polygons, etc. And then you have to think about movement directions. So do you have fixed up, down, left, right movement directions? Maybe you could move at arbitrary angles, or maybe if you have a graph, then your movement would be fixed between nodes on a graph, right? So before you even start coding a single line of code, you've got to do all this design about the architecture of your pathfinding system. All right, so here's just some illustrations of what I just talked about. Let me... where do we have this here? Oops, didn't mean to switch that scene, but I'm just going to move my camera down. There we go. Oh, wrong one. There we go. All right. So, no, I want to actually move that back. All right. So, it's going to cover up some of these labels, but the slides are on the website for students in the class. So, when we talk about pathfinding, let's look at some like visual examples of those considerations we just talked about. So this is an example of a single agent and a single goal. So we've got maybe a starting single agent over here on the left side of the map and a single goal over here on the right side of the map. So if our goal, for example, if our objective for our pathfinding system was to say minimize distance, then we would probably do something like this, right? We'd figure out a path to go from the start to the goal for a single agent. We may have a system where, and this would be something like get the player to the exit as fast as possible, right? Single agent, single goal. Here, we have an example of multi-agent single goal. So for example, you might have a game like Diablo or Path of Exile or some zombie game where you have a bunch of NPCs that are trying to get to the player, for example, to attack them. So maybe you have a bunch of these zombies and they're each trying to get to the player. So maybe your pathfinding system is multi-agent single goal, right? So with multi-agent, you could think to yourself, okay, well, multi-agent is really just a bunch of single agent searches, right? So for example, if in our single agent case, we use the A* search algorithm to get from our start to our goal, why don't we just use a bunch of A* searches to get from all of our entities to our goal? And the problem with that is that there might be a lot of these things, right? So in assignment 2, I will show you my multi-agent single goal solution that can pathfind almost I don't want to say infinite, but like hundreds of thousands of entities towards a single goal, okay? So if you're writing a game like Diablo or Path of Exile, we will be essentially writing the movement system for a game like that in assignment 2. Okay? And you don't want to do 100,000 instances of A*. Trust me, that would not run in time. You may have single agent multiple goal. So for example, try and guide this NPC toward the nearest health pack or toward the nearest weapon pickup or something like that. Okay, so depending on your problem, you're going to have to apply different space representations, different data structures, and different algorithms based on that. So what are space and action representations? So space and action representations, they're very important ideas and they're linked together. So the choice of space representation will dictate your action representation usually. So which representation that you choose is based on factors from the game's design, right? So for example, if the game designer tells you, we're writing a game where you can move in sort of any direction. Let's say, I don't know, an MMO like World of Warcraft. You can sort of have arbitrary movement turning at whatever angle that you want. Or maybe you have a game like Civilization where unit movement is on a hexagonal grid, right? So you're going to obviously have different representations for your environment based on the type of game that you're designing for. So the choice of space representation in the pathfinding engine, that will determine which movement actions can be performed as well. So if your representation is a hexagonal grid, then you're probably going to be moving on a hexagonal grid, right? If your representation is a graph, then you're probably limiting yourself to movement between nodes on a graph, etc. But let's look at some possible space representations. So this one is an arbitrary movement representation. I know what I'll do. I'll just make this a little bit smaller for now. There we go. All right. So in this example, we have this example where you have a start, you have a goal, but you can move anywhere at any angle in your game, right? So this is sort of like an arbitrary movement. You have any movement that you can do in the game. In this example, the next example, we have straight line movement. So in this game engine, maybe the designers are saying, oh, we only want the player to be able to move in a straight line. And so in order to get from our start to our goal, well, we can't walk through this obstacle here. And so we have to walk in this line and then this line to get to the goal. Maybe our game is like a roguelike or something like that, where we can only move in 4 directions, right? So in order to get from our start to our goal, we would have to move all the way down and then all the way over. So that's another type of action representation. Here we have an example, another, just like 4 directions, except we have 8 directional movement, right? So now we can move in any compass direction and the diagonals as well. So that could be our movement in the game. Next, we may have a graph representation. So if we go around our environment and we set up nodes in some imaginary graph, and then maybe we can only walk through nodes of the graph. Okay, so that may be beneficial if you have very, very large environments that you want to walk through, right? Where maybe you can't create a grid that big because the memory would be too large or something like that. In StarCraft 2, they actually have a polygonal representation. And so this is really cool because essentially what they do is they break up the environment into convex polygons. Convex meaning that you can see any part of that polygon from any part within the polygon. Okay, so here I have a convex polygon. All of these polygons are convex because if I'm right here, in this polygon, I can see any of the spots within that polygon from that spot. That's the definition of a convex polygon. So the polygonal representation is pretty cool because you know that if your start and your goal are within the same polygon, then you can just move in a straight line from one point in the polygon to the other point in the polygon, right? But if they're not in the same polygon, then what you might have to do is create a path between the polygons. So for example, if we have a starting location over here on the left, then we know we have to get over here to our goal on the right, but it's not in the same polygon. So what we would have to do is look at some level and say, okay, so this polygon is connected to this polygon, which is connected to this one, which is connected to this one. So our path for this one might look something like this, where we go down here, and then we go up, and then we go down, and finally to the goal location, okay? So this is a sort of hierarchical pathfinding system, where we have some sort of more abstract representation. So in this case, it would be a graph of polygons, and then once we get to within the same polygon of our goal, then we can just move in a straight line toward the goal, okay? So those are examples of different state representations. Okie doke. So choosing a state representation is important. And I want, just give me 1 second here. I'm going to discard all of these annotations. Perfect. All right. So choosing a state representation matters. I want this to appear. 1 second. I don't know why that's not appearing properly. There we go. So choosing a state representation matters. You see how it matters now because there can be a big difference between those things. I want to go back and change this again. Here we go. Perfect. All right. So the memory size depends on your representation. So basically, the more fine-grained or higher resolution that you choose for your pathfinding algorithm or your state representation, that is going to dictate the memory size that's necessary for your program, right? So let's just go back real quick and we'll look at some of these. So for example, if you have 4-directional movement, then you're probably working with some sort of grid-based representation, right? So in a grid, and we'll talk about this a little bit more next time, the size of your grid matters. Because what you're doing is, the size of your grid is going to dictate the resolution of your actions, right? So maybe I can move ahead 1 meter in this action space, right? In this grid space, maybe these grids are separated by a meter. Maybe in another grid, they're separated by like a centimeter. So in the centimeter grid, you have basically you're able to generate better paths because your actions are more fine-grained. But in a centimeter grid, you have way more cells that you actually have to store data for. And so in a graph, for example, maybe your representation is far more sparse and you only have to store a few nodes in the graph. So it really does have a big effect on the memory size of the running of your program and your algorithm, right? It's also going to define which actions are possible and which algorithms are applicable. So as we'll see in a couple of lectures, there are certain algorithms that are really well suited to working with grids that can't actually work on something like a graph. And so depending on your state representation, that's going to make certain algorithms possible or not to be applicable to your solution. So what you're trying to do when you choose a state representation is you're going to talk to your boss, right? Your game, not necessarily your boss, but the game designer. And you're going to say, okay, how fine-grained do you need this movement? Is movement in a grid okay? Do you want straight line movement? Do you want arbitrary movement? And then you're trying to find a balance between that path's accuracy or realism or whatever thing that the game designer wants you to implement and the computation and memory requirements that your algorithm will take to run in that space, right? So it's always a trade-off between performance, like CPU performance and memory performance versus the outcome that you want. And typically you're going to be deciding like more memory and more computation is going to give you more accurate and more realistic results. That's just a fact of life when it comes to computing. There's always that trade-off. There's never a perfect system. Typically in games, you're under very harsh technical constraints, right? You may only have a few megabytes or a few kilobytes to work with in older games. So we're going to try and choose a sparse representation in order to do easier computation. And then later what we can do is we can refine the path to look more realistic. So I'm going to go over an example of that a bit later in the lecture, but essentially we can kind of cheat. We can find a path in one representation, and then we can follow the path in another representation, which will be really interesting. So I'll show you how that works. All right, navigation meshes. So this is all leading to this thing called a navigation mesh. So what if my game has an arbitrary geometry, right? Like, you know, I can move anywhere in the game world, for example. So I'm going to need a graph structure within our environment in order to enable pathfinding. And when I say graph here, it could be a grid, it could be polygons, but it's some sort of graph structure because a graph can technically be anything, right? It's a graph structure that dictates where in the level I can pathfind to and from and what legal actions are there. So in the game industry, this is called a navigation mesh, okay? And we'll show examples of that and why it's called a mesh. So that's called a nav mesh or a navigation mesh. Most game engines, so if you go out and you get Unity or Unreal, they come with software to be able to build and edit any level's navigation mesh. So you'll be able to manually edit the navigation mesh if you want, or you can define some geometry and press a button and the game could automatically generate a navigation mesh or what its best guess at what your navigation mesh would look like. We'll get into navigation meshes a bit more later, but essentially, here's an example from an editor This is an older version of Unity, but it does a good job of showing like a level and building the navigation mesh for a level. So over here on the left-hand side, you sort of see this view of the game's geometry, and you have the entity in the game that you want to actually be moving around. So whether or not that's the player or the NPC or whatever, doesn't really matter at this point. What they do is they start with a navigation mesh that basically says, I can walk anywhere in the level, right? So this gray area. And then they use a tool to sort of cut out parts of the level where they don't want the player to be able to walk, right? So that is the formation of the navigation mesh. And just because it's a square grid here doesn't mean it's not a graph, right? The graph is essentially saying that you can walk between connected areas of that grid. So what the designer here or the level builder here says essentially is, well, maybe I don't want the player to be able to walk right up against these towers, right? So I'm going to cut out the navigation mesh one grid away from those towers. And then the player can essentially only walk on those gray or, well, essentially blue areas here. And then what the designer does is it says, well, there's this little sort of hedge or wall in between these two areas. And so then the designer can make links that say, okay, well, the player can actually navigate from this part of the flat navigation mesh up to that part on the top of the hedge. So that would dictate, okay, when your pathfinding system is going through, it says you can go from this part up to this part, but you can't jump over any other parts, all right? So that's what it means. You can also have a navigation mesh that is not just perfectly flat, right? So here we have an example from a game where you may be a spider or something like that, and the spider can like walk on the walls or the ceiling. And so here you're defining, okay, this navigation mesh, the player can walk here. All of these blue areas can essentially be walked on. So you can see that the player or NPCs, whatever they're defining here, can walk on like the flat side of this little wall, but maybe not on the side of that little wall or near the corners of the wall, right? So you're defining that navigation mesh. Here's a little bit more of a complex example where you want the player, maybe the player in this game can't jump, right? But you want them to be able to sort of automatically leap between pillars, for example. So this is like almost like a Legend of Zelda game, right? Where you can't manually jump, but if the space between two ledges is small enough, if you walk forward, it will automatically do a little bit of a hop for you. So this is how you can implement something like that with a navigation mesh. So on the floor here, you see the nav mesh that says you can walk anywhere on the floor. You can walk on the top of these things, but you can't walk on the side of them. And what these little things are, these nodes here say that when you walk on top of this part of the navigation mesh, it will hop you over to this part of the navigation mesh. So the navigation mesh, depending on your game engine or your pathfinding system, can have all of this sort of semantics built into it, where you define nodes that say, okay, I can jump from here to here, I can move on this surface, I can't move on that surface. So that navigation mesh is essentially just showing you where in the game that you can actually traverse, okay? And then your algorithm would look at that navigation mesh, see which actions are possible, and then figure out the path that you can traverse to get an NPC from one place to another, for example. So that's what navigation meshes are. They're intuitively quite simple, but their implementation may be a little bit complex. And in assignment 2, we will be writing our own sort of simple navigation mesh system, which I'm excited about. So here's the pathfinding workflow now. That your boss has come and said, I need you to write the pathfinding for the game. Now you know what you have to do in order to do that. So the first thing you have to do is identify the problem that you're solving. Let me edit this. There we go. So first, identify the problem that you're trying to solve, right? Is it single agent, single goal, multi-agent, multi-goal, all this kind of stuff, dynamic, static, all that. You have to just identify the problem that you're solving. Second, you have to construct a space representation. So you have to decide on which space representation is good for you and good for the designers. Then you have to decide which actions are possible within that representation. Can the player jump? Can the player move arbitrarily up, down, left, and right? Then at some point in the running of the game, you're going to be given a start and a goal location, right? So for example, we want all the zombies in the game to run toward the player, or we want the player to run toward the exit, or we want the NPC who you're escorting to follow the player, but also attack things that get into within attack range, right? So you're given some sort of goal that you have to accomplish. Then you have to apply an algorithm which finds the path for you, and then you have to actually follow the path from the start to the goal. And I know that like this seems, maybe it wasn't so obvious, and it seems kind of tedious, but it's all super necessary, right? If you go play a video game and then try and think about all this, right? Like go load up Path of Exile, or go load up Diablo, or go load up World of Warcraft, or whatever game that you're playing, and try and, like, it's a good mental exercise, right? To go and say, okay, what problem were they trying to solve? Well, it looks like in this game it was this. What space representation do you think they were doing? What actions are possible, right? And which algorithm do you think they're using? It's cool to load up a game and think about like what's actually happening behind the scenes. So let's do a little bit of an example here with this sort of, three-dimensional structure here, like some platforms or something. So the first thing we're going to do is choose a space representation, right? First thing we have to do is identify the problem. So let's say that we want to do single agent, single goal. Okay, that's just the simplest possible case. Step 2, construct a space representation. So let's say we're going to use polygons, right? And so movement within this system, so a polygonal-based system is still just a graph-based system. It's just that the nodes of the graph represent maybe the center of these polygons, right? So this is chopped up into convex polygons, and then we are going to be moving from C1 to C8 here, okay? So we've been given this start and this goal location. Then we've decided that our actions are moving between connected polygons here. So that's our graph. So we're going to run our pathfinding algorithm, whatever that may be. And here's the path that we're going to take. But now what we have to do is translate that path in the space of polygons to actually follow the path in the space of like game pixels, right? So a path that we may want to actually follow, or, the path following problem may have the player looking something like this, like cutting corners, moving in straight lines, etc. So the player would then move through that path, and that's the path following. But how do we do the path following? That's really the part that we haven't discussed yet. So now that we have a path, right, we've chosen a space, we've chosen actions, we've chosen an algorithm, how do we actually make our agent traverse through it in the game, right? So the simplest way that I've found for this is to use a waypoint system. So essentially, each point along the path, consider that to be a waypoint. And you're going to choose waypoints so that the path between each waypoint is always clear, meaning that waypoint 1 will always have a clear line of sight to waypoint 2. Waypoint 2 has a clear line of sight to waypoint 3. And then all you have to do is walk from one waypoint to the next waypoint, and then stop when the NPC reaches the goal, or when they're out of waypoints, okay? So let's just have a look at this case in the case of a grid, right? So we're very familiar with this because we did COMP4303, where we have a starting location. Let's say we've chosen a grid for our representation, and then what we did is we found a path. And that path, each movement along that path, each action, we've created a waypoint, right? So what we're going to do in order to do the actual path following is we're going to move from here to here. That's the first waypoint. Once we've reached the first waypoint, we go to the second waypoint. Second waypoint, we go to the third waypoint, to the fourth, and so on and so forth until we actually get to the goal from the final waypoint. Okay, so this is a very simple example of actually doing path following in games. So path finding, that's sort of the algorithmic side of finding the path, and path following is how do we actually make our character walk the path in the game. Let's do something interesting here. That's a lot of waypoints, right? Let's say every second step or every second action was a waypoint. So now what we do is we have fewer waypoints to follow. So here, maybe we go to this waypoint, then to this one, then this one, this one, this one, this one. So the same path, but half the waypoints. Now let's talk about something that I briefly mentioned before, which is called path refining. Okay, so in path refining, what we do is we take a previously computed path and we make it a little bit better. Okay, so let's say that our game engine allows for arbitrary movement. So if our game engine allows for arbitrary movement, why would we choose a grid representation for our algorithm? Okay, well, we could choose a grid representation and then implement path refining. So here, we had this sort of blocky up, down, left, and right movement, right, to follow our waypoints. But I said before that waypoints could be chosen such that there's just a clear line of sight between them. So let's do the following thing. Let's choose the furthest away waypoint that we still have a clear line of sight to. So this waypoint here, let's just go in order of the waypoints. So we go to the first waypoint, still have line of sight. Second waypoint, still have line of sight. Third waypoint, still have line of sight. Fourth waypoint, no longer have line of sight. So we go back to the last one that we had line of sight. So we could do a waypoint system like this, and this is called path refining. Let me move this down here. Okay, so this is called path refining. And we can see here what we have now is a much faster path because we can just go to this waypoint and then to the final goal. Or we could apply some sort of smoothing behavior so that now, even though we've used a graph to implement our pathfinding, right? Sorry, we've used a grid to implement our pathfinding, which is a type of graph. We have a smooth movement behavior from the start to the goal. So what we did was we chose a grid representation. We ran a grid-based pathfinding algorithm. But now that we have a path, we're going to refine the path. This is path refining to smooth out the behavior, to get a more realistic path from a start to a goal. How do we smooth out that behavior? Well, if you took Computer Science 4300, maybe you know what I'm talking about, but this is a steering behavior, okay? So let's go and talk about steering behaviors. All right. So come on, PowerPoint, you can do it. All right. Steering can be seen as a framework for controlling autonomous agents, such as robots, CGI in movies, NPCs in games, etc. So steering can be used as a path finding step, but we're going to be using it as a path following step, okay? So steering adds more realism and fluidity into the agent's movement and can enhance the experience, right? So essentially what steering is going to do is we're going to take situations in which we have straight line behavior. Like, for example, if I'm moving here and then instantly turn to move here, instead, steering is going to smooth out that behavior so we have a more realistic curve. It's literally steering in a car, right? So think of how would a car drive this path, and that's what steering implements, okay? Steering can be really fun to implement. I love implementing steering because there's so many cool parameters to play around with. The effects that you can produce are really neat, and the mathematics is so simple. So, at its core, steering essentially smooths the movement of entities in games. It can be enhanced to do more than that, but really its core behavior is to smooth the movement of entities in games. So if we change directions instantaneously or stop on a dime, all this kind of stuff, it can look really bad in games. And so what steering does is it acts as a sort of force. So we'll actually have a steering force that smoothly guides our entity, whether that's the player or an NPC, toward a target. And steering will be part of assignment 2. Okay, you will have to implement steering to get full marks in that assignment. All right, so what is a steering behavior? All righty. Let's say we have some entity in our game, and if you did Computer Science 4300 with me, then this is going to be a little bit of a repeat, but it's pretty quick, so it's not so bad. So we have an entity in our game. Say it's this like this player down here or whatever it is, and it has a current velocity. So the velocity is the X and Y change per frame, right? Like for example, here I'm moving, so if this is my, if on one frame I'm going to be right here, and the next frame I'm going to be right here, then this is the X change of the object, right? And this is the Y change of the object. So the velocity is represented by XY, which is the change in the object's position each frame. Now, let's introduce a little bit more complexity. Let's say that yes, our entity is currently heading in that direction, but something happens that makes it want to go in this direction toward a target, right? So maybe you're moving around, you're playing the snake game or something, and the apple spawns and you want to go toward that. Or you're walking around in an MMO and a chest spawns and you want to go toward the chest, right? So I have a current velocity, but now I have a new target that I've chosen that I want to go towards. So if I don't have steering, well, this is going to be, this is my current velocity, a straight line. I'm moving in a straight line. And then on the very next frame, I'm going to instantly shift, right? I'm going to turn on a dime and instantly shift toward moving toward the target. But that doesn't look right. Think of it as a car. Can a car instantly shift? No, it can't, right? It has to turn at some turning velocity toward a target. So if this is the desired direction toward the target, then this red vector is our desired velocity, right? Because we have a current velocity. The length of that velocity is our current speed, right? So velocity implies direction and magnitude. Speed is just the magnitude. So as we're turning, as we want to go toward our target, we want our speed to stay the same. So even though this long red vector is where we eventually want to go, the update that we do every frame is this desired velocity, which has the same length. So the red vector here should have the same length as the blue vector. So how do we calculate the desired vector from the target and the current velocity? Okay, well, this is actually pretty easy. So we're calculating this desired vector, keeping the same speed from our current vector. So what we do is we first calculate this red dashed vector, so the entire vector, right? So we're going to take pause here is our current position. So pause is our current position of our entity. So in order to get the vector from a current location to a destination, we subtract the current location from the destination. So if our destination is target, which is an XY position, and our current location is pause, which is an XY position, then our desired vector, which is initially this dashed red vector, is just target minus position, okay? And that gives us, that long dashed red vector. Then what we have to do is we have to normalize that vector in order to get it to length 1, okay? So we normalize it, and to normalize a vector, you divide each component of the vector by its length, all right? And then now what we have is we have this red vector, but with length 1. And now what we do in order to convert it to the same length as the blue vector, since it's of length 1, we figure out the length of the blue vector, and then we multiply the x and y component of the red vector by that length. So we get the whole dashed vector, we normalize it to length 1, then we multiply it by the length of our current velocity vector. And so then what we have is this desired red vector, which has the same velocity as the blue vector, okay? So if we were implementing turn instantly, turn on a dime movement physics, then what we would do is we would change our current velocity to the desired velocity, okay? But that's not what we want. We want a steering behavior. We want it to be more smooth, right? Okay. Question out there, if we have the red vector, why do we have to make it length 1? So this is a bit confusing, but the first step gives us the dashed red vector, this really long one. And what we want to do is we want to change the length of this big vector to be the same as the blue vector, okay? So in order to do that, we first normalize this vector to get it to length 1, and then we multiply it by the length of the blue vector, which is 1 by this length, which gives us the correct length. Okay, so it's very difficult to sort of, I've put 3 steps here. It makes it look like we already have the red one, but we don't. The red one is the final outcome of this. That's a good question, though. So far, we've calculated the desired vector from the target. Okay, now let's talk about how we would implement a steering behavior. So what we first do is we're going to calculate a vector called the steering vector. And the steering vector wants to take us from our current destination, which is like the end of the velocity vector, to the end of the desired vector, right? So this steering vector is going to act as a force which takes us from where we're currently headed to where we eventually want to be headed, right? So in order to get, again, a vector from the current location to a destination, we take the destination and we subtract the current location. So we subtract desired minus velocity, and this gives us steering, okay? However, we don't want to just go all the way, right? If we went vel plus steering, we would get all the way, and that would be turning on a dime. So what we want to do is we want to scale the steering vector to make us head part of the way toward the desired vector, but not all of the way toward the desired vector, okay? And we call this vector the steering force. And depending on how long this green vector is, that is how strong the steering force is. So if the steering force is 0, we won't turn at all. If the steering force is 1, we will instantly turn all the way. And if it's like 0.1, then we're going to be turning like 10% of the way each frame. And what will happen is, I've called this black vector here actual. So what that means is we've got our current velocity. We're going to scale the steering force that heads us toward the desired velocity. And when we make the change from our current velocity toward and actually do the steering, that is the actual velocity that we will be going on the next frame. Okay? So how do we calculate this actual vector? Well, the first thing we need to do is we need to determine some sort of scale factor. So as I said before, this dashed green line here is the steering force. If we had a steering force of 0, then that green vector would have a length of 0. Right? It wouldn't take us anywhere. If it had a length of 1, then it would take us all the way to where we want to go, and it would be an instantaneous shift, and that's not what we want. And so here in this graph, it looks like this steering force is approximately like 0.3, right? Because it's about a third of the way across, right? So that's what this steering force is. So now when we go to do our actual calculations, we've got this scale value down here. The scale value is a number between 0 and 1. It's whatever we happen to choose. So whenever you implement your steering, you're going to put in something, and I recommend starting with like 0.01, something very small, because you're going to be steering on every frame, and you don't want to like just steer too quickly. So start too slow and then adjust this value. So that value is going to be based on like what your game designer thinks is a good value. You'll go and you say, do you want 0.1, 0.0001, something like that. You'll show them the behavior and they'll tell you, okay, make them steer a little bit faster. You'll turn the speed up. Make them steer a little bit slower. You'll turn the scale down. Okay, so that's what that is. So we're going to calculate first the dashed green complete steering vector. That's, again, desired minus velocity. Then we're going to calculate steering. Okay, that is this green vector, the non-dashed vector. And what we do to calculate that is we just multiply the steering vector, the dashed green line, by the scale. And so the actual vector that we want then is velocity, that gets us to the end of the green point, plus steering will give us this actual vector, okay? And that is our steered velocity. So on the next frame of the game or whatever, that's the direction that we'll be going in. So if we want this steering math, let me move this real quick. All right. If we want the steering math, I've got a diagram up here for you with so I can have everything on this one nice slide. So we have to be given the following things. We are given our current velocity. That's where we're currently headed. We're given our position. We're given the target, and we're given a scale. So that's the steering scale force. First, we're going to have desired equals target minus pause. So that's the dashed red line. Then we divide desired by its length to get a normalized desired vector of length 1. Then we multiply desired by the length of our current velocity to get the red vector equal to the blue vector in length. Then we calculate the dashed green line, which is desired minus velocity. Then we scale the steering force to be however strong we want it. And then we add the steering force to our current velocity to get the actual vector. Okay, so that is the entire process of steering. It's very, very simple. Like the hardest part of this entire thing is the length function, which is just Pythagoras, right? It's the distance between the 2 points. All right, so we have different types. I've got this moving around of the camera is getting annoying. I'll just stick to this for now. All right, so we can have different types of steering as well. Steering makes the most intuitive sense when you're talking about moving toward a target, right? So when we move toward a target and we smooth steer toward our target, that's called seeking behavior, okay? So we are seeking the current location of the target. However, that's not the best way to catch up with something, right? Seeking is sort of like a homing missile. It's going toward where we currently are. But if you actually want to catch up with something, you want to go to where it will be, right? Not where it is. And so there's another type of steering called pursuing behavior. So if you pursue, then you're trying to sort of estimate where the target will be and then head in that direction. So here, if we somehow know the target's velocity and we add that target velocity to the position, and then that becomes our new target, that is called a pursue behavior. So that's another type of steering. Finally, we have a fleeing behavior. So you can use steering to run away from things as well. Oh, just give me 1 second. I've got a visitor at the door here. Here we go. Luna really wanted to say hi. She was banging at the door there. So Luna implements a steering behavior toward treats in the house. Definitely a pursuing behavior. Say hi, Luna. Hello. Okay. So she's gone to find the treats in the room that she wants. Okie doke. Back to the PowerPoint. So yeah, Luna is the seeking behavior or the pursuing behavior, except when someone visits who she doesn't know, and then she implements a fleeing behavior, right? Because she's really scared of new people. So in a fleeing behavior, all you have to do is multiply this desired behavior by -1. And then instead of going toward a target, you're steering away from a target, right? So if this target appears and you're heading towards it, it will actually steer away from it. And all you have to do is change the desired position. That's it. Really, really easy. Now, one thing that can go awry with your steering behaviors is what happens when you actually get close to the target. So one issue with steering is that when you get close to the target, your entity will oscillate back and forth, okay? Because what happens is you're currently like on this side of the target, and so you're steering in this direction, but then when you go a little bit past the target, it steers backwards, and so you get like, if this was the target right here, this bottom left corner, I guess I'll just use the actual target, it's going to like move past, then come like this, and then like oscillate back and forth, okay? And so that needs to be fixed somehow. And we do that with what's called an arrival behavior. So the simplest solution to an arrival behavior is to just scale the speed as it approaches the target within some distance, right? So what we do here is that we don't go full speed into the target. Picture that you are pulling into a parking spot at the Avalon Mall, right? There's a bunch of psychos driving around you. You're going down the road at like 50. You turn into the parking lot. As you arrive at your destination of your parking spot, you're probably not jamming it in there at 50, right? If you can, then good on you. But actually, come to think of it, that's probably how most people in St. John's Park. But you shouldn't be jamming it in there at 50, right? You should slow down as you approach your arrival. So that's just one of the things that we do is as you're doing steering, if you actually get to your destination, define some sort of distance from your goal where you say, okay, now I'm going to start slowing down. And you just start scaling it with that. So there's no best values to this sort of arrival behavior. This is completely dependent on what your game designer thinks is good, right? So you show them something, you tweak the values, they say whether or not they like that. So here's some actual examples now that we've talked about the math of steering behavior. Here is a steering seeking behavior. So in this example, we have like little Luna here, right? Looking for treats. And so as we change the desired position, you can see that she is slowly turning toward the target rather than just turning on a dime toward their target, right? So this looks a little bit more like what a cat would actually do. It can't just instantaneously turn in 16 milliseconds, right? It has to slowly turn toward a target. Cool. All right. You can also use steering for avoidance behaviors, okay? So say we're making like a hockey game and we found a path. Well, we could use steering to follow that path, but also make micro adjustments to say, go between these players, right? If you think about it, this is kind of what I think your brain is doing when you're playing a sport like hockey or soccer or whatever. You want to go toward the goal, but as you are moving toward an enemy, or even a teammate, you're trying to avoid a collision, right? So this is called like avoidance or avoiding collisions. So you can use steering to just say, gently turn me away from things that I don't want to be next to. And the outcome of this can be quite dramatic, actually. So here's an example of multi-agent pathfinding that uses steering to avoid obstacles. So these blue ones are trying to avoid the white ones, and the white ones are trying to avoid the blue ones, and they get stuck for a little bit, but in the end, the steering does guide them in a way that sort of separates the two things, so there's a path for one and a path for the other, right? So steering can be used for this sort of thing. But remember that it's more of a path-following thing than it is a path-finding thing. You can use steering for the whole thing, but your paths won't be as good as if you combine it. If you want to watch some more steering demos, there's this really great OpenSteer package that you can download. I recommend just, playing around with that. But we will be implementing steering in assignment 2 in order to get full marks. So keep that in mind and just think about how you might want to implement steering in your pathfinding system. Cool. So let's discard that. If you're watching this live, the quiz is now live. So go do the quiz as soon as you want. It is the quiz is on this lecture that we just did and the previous lecture, which was assignment 1. And make sure that you get that in there by Sunday at 11:59. All right, great. That's all that I have for today. Thank you very much, and I'll see you in the next one.